High in the San Juan Mountains of Colorado, surrounded today by some of the most spectacular scenery in the Rocky Mountains, the landscape gives almost no indication of the violence that once took place here. There is no towering volcanic cone like Mount St. Helens, no broad plume rises into the sky, no lava glows beneath the snow. Instead, there are mountains, valleys, forests, and exposed cliffs of ancient volcanic rock. Yet hidden within those rocks is evidence of one of the most extraordinary eruptions known anywhere on Earth. Roughly 28 million years ago, an enormous volcanic system in southwestern Colorado released a quantity of magma so immense that it transformed an area covering thousands of square miles and collapsed the roof of its own magma reservoir. The eruption created what geologists now call the Garita Caldera and produced the Fish Canyon Tuff, a volcanic deposit with an estimated volume of about 5,000 cubic kilometers, or roughly 1,200 cubic miles. That places the event among the largest explosive eruptions recognized in Earth's geological record. The name Garita Caldera can sound deceptively modest. A caldera is simply a large volcanic depression created when the surface collapses into a partially emptied magma reservoir. But Garita was not a small volcanic crater. Geological studies indicate that the collapsed structure was approximately 75 kilometers by 35 kilometers, or about 47 miles by 22 miles, although different reconstructions produce somewhat different dimensions. Another reconstruction places the caldera at roughly 80 kilometers by 30 kilometers, or about 50 miles by 19 miles. Either way, this was an enormous volcanic structure. Much of its original shape has been heavily modified by erosion, later volcanic activity, and the relentless uplift and sculpting of the Rocky Mountains, making it difficult to recognize today as the remains of a single colossal volcanic event. The real scale becomes easier to appreciate when the eruption is viewed not as a hole in the ground, but as a gigantic transfer of material from the Earth's crust to the surface. 5,000 cubic kilometers is not simply a large amount of ash. It represents an immense volume of hot, silica-rich magma that was fragmented, expanded, and transported as pyroclastic material. The Fish Canyon Tuff spread across an area exceeding 10,000 square kilometers, or nearly 4,000 square miles, according to geological studies of the eruption. In some locations, the resulting volcanic rock accumulated to extraordinary thicknesses. At Garita Mountain, for example, the exposed Fish Canyon Tuff is more than 1 kilometer thick, or more than 3,300 feet. What now looks like ordinary mountain rock is therefore part of the frozen remains of a volcanic catastrophe that occurred tens of millions of years before humans existed. That distinction is crucial because the phrase supervolcano can create the wrong mental picture. It is tempting to imagine a giant underground chamber filled with liquid magma sitting beneath Colorado today, waiting for the next enormous explosion. That is not what the geological evidence shows. The Fish Canyon magmatic system was active during the Oligocene epoch, around 28 million years ago. The magma body that fed the eruption evolved, crystallized, and ultimately solidified. What remains today is its geological architecture: enormous bodies of intrusive rock, volcanic deposits, altered minerals, collapsed caldera structures, and younger volcanic rocks that allow scientists to reconstruct the system long after its magma was gone. The buried remains are therefore a geological fossil of a supervolcanic system, not evidence of an active supervolcano preparing to erupt. To understand why the eruption became so enormous, scientists have had to reconstruct what was happening underground before the catastrophe. The Fish Canyon magma body was not simply a cavern filled with perfectly liquid molten rock. Research indicates that it was an enormous upper crustal magmatic system dominated by crystal-rich dacitic magma and, in its later stages, a largely crystalline mush. The erupted material contained roughly 68% silica by weight and was exceptionally rich in crystals. Those crystals included feldspars, quartz, hornblende, biotite, and other minerals. This may seem like a technical detail, but it changes the way scientists understand the eruption. The magma reservoir was a dynamic, evolving body in which crystals were growing, dissolving, and being rearranged as new heat entered the system. The concept of a crystal mush is particularly important. For decades, Popular images of volcanoes often depicted magma chambers as enormous underground lakes of liquid rock. Modern petrology has shown that many large silicic magma reservoirs are far more complicated. Much of the material may consist of interlocking crystals with smaller quantities of melt occupying the spaces between them. Such a system can remain relatively stable for long periods and then become mobile when heat, fluids, or new magma disturb the balance. In the Fish Canyon system, researchers found evidence that the enormous magma body was rejuvenated by the introduction of hotter, more mafic magma from deeper levels. That additional heat helped remobilize portions of the crystal-rich reservoir and may have played a critical role in preparing the system for eruption. The geological record becomes even more remarkable when scientists examine what happened immediately before the main eruption. The Fish Canyon Tuff did not appear out of nowhere. It was preceded by the eruption of the Pagosa Peak dacite, an unusual deposit with a volume exceeding 200 cubic kilometers, or roughly 48 cubic miles. In places, this material reaches thicknesses approaching 1 kilometer, or about 3,300 feet. Unlike a conventional explosive eruption dominated by highly fragmented pumice and ash, the Pagosa Peak material behaved in unusual ways. Some of the hot, viscous pyroclastic material moved and accumulated almost like lava. It welded together while still extremely hot, and in some locations underwent gravitational spreading. That earlier phase may have been the warning signal of a much larger failure developing inside the volcanic system. Geological studies indicate that the Pagosa Peak dacite and the Fish Canyon Tuff were compositionally similar, suggesting that both came from the same enormous magmatic system. The earlier eruption appears to have involved a relatively low eruption column and unusual fissure-fed activity. As magma was withdrawn, the structure supporting the roof of the magma reservoir was progressively destabilized. Eventually, the system crossed a threshold at which collapse became possible. The roof of the enormous magma chamber began to fail, and the main Fish Canyon eruption followed. Once the Fish Canyon eruption began, the physics became vastly different from that of an ordinary volcanic eruption. A large explosive eruption is driven partly by the rapid expansion of dissolved gases as magma rises and pressure falls. Silica-rich magma is also comparatively viscous, making it difficult for gas bubbles to escape efficiently. When the magma fragments, the expanding mixture of volcanic gas, ash, pumice, and rock can accelerate dramatically and produce pyroclastic density currents. These currents are not simply clouds of ash drifting through the atmosphere. They are dense, turbulent mixtures of hot gas and volcanic particles capable of racing across the landscape and filling valleys. During the Fish Canyon eruption, the scale of this process was multiplied to an almost incomprehensible degree. The result was the Fish Canyon Tuff, one of the largest ignimbrites known on Earth. An ignimbrite forms when enormous volumes of pyroclastic material are deposited from hot, ground-hugging flows or currents. As the material accumulates while still extremely hot, particles can weld together. Over geological time, cooling and chemical alteration transform the deposit into solid volcanic rock. The cliffs and ridges now exposed in the San Juan Mountains are therefore the fossilized remains of currents that once moved through the region, carrying vast quantities of hot volcanic material. What appears today as a massive, relatively coherent rock formation began as an extraordinarily mobile mixture of fragmented magma, volcanic gas, and pulverized rock. The amount of material involved is what places La Garita in the supereruption category. Scientists use several methods to compare ancient eruptions, including the volume of erupted material and the magnitude of caldera collapse. The Fish Canyon event, with an estimated erupted volume around 5,000 cubic kilometers, or 1,200 cubic miles, was vastly larger than famous historical eruptions such as Mount St. Helens in 1980. It was also substantially larger than many eruptions that dominate modern discussions of volcanic hazards. The United States Geological Survey describes the La Garita eruption as one of the largest eruptions known on Earth. Even the comparison with Yellowstone needs careful treatment. Yellowstone is famous because of its enormous prehistoric eruptions, but it does not hold the record for the largest volcanic event in the western United States. The United States Geological Survey has specifically noted that the La Garita eruption was larger than the eruption that formed Yellowstone caldera about 631,000 years ago. The Fish Canyon eruption also exceeded the volume of several other famous caldera-forming events. In other words, the geological history of Colorado contains a volcanic event that rivals and in some measures exceeds the scale associated with the world's most famous supervolcanoes. Yet the greatest surprise may be what happened after the eruption. The collapse of La Garita did not mark the end of volcanic activity in the region. Instead, the central San Juan Mountains became the setting for a remarkable sequence of additional caldera-forming eruptions. Geological mapping has revealed that multiple calderas developed in and around the La Garita Depression. Some were nested within or overlapped the earlier structure. Within roughly a million years, at least several additional explosive eruptions occurred in the broader central San Juan caldera cluster. The region effectively became a giant volcanic laboratory in which multiple generations of magma reservoirs repeatedly formed, evolved, erupted, and collapsed. The scale of this volcanic province is difficult to grasp from the modern landscape. The San Juan volcanic field covers approximately 25,000 square kilometers, or nearly 10,000 square miles. It contains remnants of numerous volcanic centers, thick ash flow sheets, and large calderas. The major volcanic activity occurred during the Oligocene, when the region was part of a much larger volcanic environment associated with the tectonic evolution of the western United States. The San Juan Mountains that exist today are therefore not simply mountains that happen to contain a volcano. They are the heavily eroded remnants of an ancient volcanic province whose eruptions repeatedly reshaped a substantial part of the southern Rocky Mountains. The reason these volcanoes developed in this part of Colorado is connected to the deeper tectonic history of western North America. During the Oligocene, the region experienced major magmatic activity associated with the changing geometry of subduction and extension in the western United States. Earlier volcanic centers had already erupted intermediate composition lavas and breccias. Later, the volcanic system shifted toward enormous silicic eruptions. The result was an ignimbrite flare-up in which huge quantities of evolved magma accumulated within the crust before being released in enormous ash flow eruptions. La Garita represented the climax of one of the most spectacular phases of this ancient volcanic activity. Scientists have learned much of this history by studying minerals that are microscopic clocks. The rocks contain minerals whose radioactive isotopes decay at known rates. By measuring isotopic ratios, researchers can establish when crystals formed and when volcanic deposits cooled. The argon dating work at La Garita has been particularly important because it refined the timing of events surrounding the eruption. A 2019 study using 40 argon and 39 argon geochronology found evidence for an approximately 100,000-year eruptive history associated with the Fish Canyon magmatic system. It identified a roughly 60,000-year period of pre-caldera eruptive activity, followed by a possible hiatus of as much as 20,000 years before post-caldera activity. That finding changes the popular image of a supereruption as a single instantaneous event that begins without warning and ends almost immediately. The main catastrophic eruption may have been geologically brief, but the magmatic system that produced it had a much longer history. Magma accumulated, crystals formed, heat was transferred, earlier eruptions occurred, and the reservoir evolved over tens of thousands of years. The eventual collapse was therefore the culmination of a long-lived magmatic process rather than an isolated event disconnected from everything that came before it. Another clue comes from the minerals themselves. Researchers examining crystals from the Fish Canyon system have found evidence of repeated growth and resorption. Some feldspar crystals show changes in composition toward their edges. Quartz crystals display textures suggesting that they were partially dissolved and later regrew. Hornblende crystals also record changes in their chemical environment. These microscopic features reveal that the magma chamber was not static. Crystals experienced changing temperatures, pressures and chemical conditions before finally being swept into the eruption. The most important discovery may therefore not be a gigantic empty chamber hidden underground, but a complex record of how enormous magma reservoirs actually work. The Fish Canyon system demonstrates that a massive magma body can exist as a dynamic mixture of crystals, melt, and fluids. Heat from deeper magma can rejuvenate portions of the reservoir. Crystals can record these changes. Magma can move through the crust, become concentrated, lose heat, crystallize, and then be remobilized. Eventually, structural failure and magma withdrawal can destabilize the roof of the reservoir and trigger caldera collapse. There is also a striking geological paradox at La Garita. The eruption was so enormous that the magma body itself effectively revealed its hidden architecture by destroying its roof. The collapse created a gigantic depression, while later erosion stripped away portions of the volcanic pile. Subsequent tectonic uplift raised the region, allowing geologists to examine rocks that were once buried deep within the volcanic system. Instead of relying solely on modern geophysical instruments to infer what might exist kilometers below the surface, researchers can study the ancient plumbing system directly because geological processes have exposed fragments of it at the surface. La Garita Mountain is one of the clearest examples. Rising to about 4,179 meters, or 13,711 feet, it is not a conventional volcanic peak formed by successive lava flows around a central vent. USGS describes it as a resurgent block of Fish Canyon Tuff more than 1 kilometer, or roughly 3,300 feet thick. The top has been eroded and the base is not exposed. In other words, a mountain that looks like part of the modern Rocky Mountains is actually a gigantic piece of material associated with an ancient caldera system. Large calderas can experience renewed uplift after collapse as deeper magmatic and structural processes modify the depressed area. At La Garita, later deformation and erosion have dramatically altered the original landscape. The modern mountains should therefore not be mistaken for a pristine caldera rim. They are the product of millions of years of erosion, uplift, faulting, and subsequent volcanic activity. The volcanic structure visible today is only a fragment of what existed 28 million years ago. The enormous volume of Fish Canyon Tuff also raises an obvious question. Where did all that magma come from? The answer is not a simple underground reservoir that slowly filled like a tank. Studies of the Fish Canyon magma body suggest that the system had batholithic dimensions, meaning it was comparable in scale to the large intrusive bodies that form substantial portions of continental crust. Much of this magma never erupted. It crystallized underground, leaving behind intrusive rocks that represent the frozen roots of the volcanic system. The material that erupted was only the portion that became sufficiently mobile and was connected to pathways capable of reaching the surface. The geological record also shows that the aftermath of such an eruption can last much longer than the eruption itself. The collapsed caldera becomes a new geological basin. Hydrothermal systems develop. Later magma can exploit fractures created by the collapse. New volcanic centers can form. Rivers erode the deposits and transport volcanic sediment into surrounding basins. Mountains rise and are stripped away. Millions of years later, the original volcanic landscape may have almost completely disappeared, while fragments of the eruption remain scattered across a huge region. This is why Fish Canyon Tuff can be found far beyond the immediate vicinity of La Garita. The eruption produced an extensive ash flow sheet, and geological mapping has traced its remnants across thousands of square kilometers. Some deposits have been deeply eroded or buried, while others remain prominent in mountain outcrops. The distribution of those rocks acts almost like a geological fingerprint. By mapping them, scientists can reconstruct the direction and extent of the ancient pyroclastic flows and estimate how much material was released. Perhaps the most unsettling fact about La Garita is not that it could erupt again, because there is no evidence that it is preparing to do so. The unsettling fact is that the Earth has produced eruptions on a scale far beyond anything witnessed by human civilization. The San Juan Mountains are a reminder that the planet's volcanic systems can occasionally accumulate and release enormous quantities of magma. The evidence is not hidden in some mysterious underground chamber. It is sitting in plain sight, carved into cliffs and ridges across Colorado.